All right, so this is what's called the semi-major axis. That, as I said, is going to be very important to us for Kepler's third law. All right, so let's get to the second law. The second law, this is the original way that Kepler had worked it out, with, of course, using Tycho Brahe's data. What he found is that, so take a look at this picture. Let me read this. All right, so basically the area A, all right, so this shade, this area right here in kind of a light blue color, and area B and area C are the same. They're exactly the same area, all right, and the time the time for the planet to go from right here, at the beginning of A, to the other side of A, this little arc right here, is exactly the same time that the planet goes in the arc that makes B, and this exactly the same time, although this is a little exaggerated, for the time to go for this little arc C. So basically, what he determined, this is the way he said his second law of planetary motion is, Kepler that is, of course, is that a planet sweeps out equal areas. Okay, so that's why A, B, and C are equal in area in equal times. So the time it takes to sweep out these areas is equal. A better way to say this, okay, the way, and I mean it's true either way, but a better way to say this is then when the planet, of course, because it's in an elliptical orbit, it's going to be times when the planet is further from the sun and closer to the sun, right? So that happens, of course, and when the planet is furthest from the sun, it's moving slowest. When it's closer to the sun, it's moving faster. Or the fastest. Okay, so that's another way of saying Kepler's second law. Equal area in equal times, or faster when it's further from the sun, and slower. Sorry about that. Slower when it's further from the sun, and then fastest when it's closer to the sun. All right. Well, and then the final law. So he just had three laws of planetary motion. So the third law, it actually took him a long time to work this out, because certainly he didn't have a calculator, for 400 years ago, he had to do all these calculations by hand, and it still amazes me today that he was able to come up with this. So what he discovered is the period, which is represented as a P. All right, so it's a P for period in units called years. Well, in years. That is proportional, mathematically proportional to the cube. So the third power of the semi-major axis. And the semi-major axis is measured in astronomical units. For example, for the Earth, that's one astronomical for the Earth, one astronomical unit, I should say, for the Earth. And of course you cube that, so 1 cubed, of course, is still 1, and then 1 year, 1 squared is, of course, still just 1. So 1. But that's true for all of these, for all the planets, even planets that were discovered, after the time of Kepler. All right, and really this is true for any object that is orbiting the sun. So it follows this the fact that the period squared is proportional to the semi-major axis cubed. All right, so that is that one. There's another quantity called eccentricity. So the more oval or egg-shaped the orbit, the more off from being a circle, the more eccentric it is. It turns out that Mars, the planet that Kepler used to come up with his laws of motion, is actually has a pretty eccentric orbit, and you know the observations that Tycho Brahe had made, the naked eye observations, really, he wouldn't have got the Kepler would not have been able to figure this out, figure out the three laws of planetary motion, without the fact that without Tycho Brahe's observations of Mars. If he had looked at other planets, he would have gotten, the data would have been indicating that a planet was moving in a circle, and not an ellipse, and that's just because of observational error, right? Because using the naked eye is certainly not as accurate as using telescopes. All right, here's a couple of other. Perihelion is when a planet is, or any object really, comets do this as well, when it's the closest to the sun. Aphelion is when it's furthest from the sun. Okay, so those are some terms we need to know. So again, an astronomical unit is the distance the Earth is from the sun. So we use that. Let's go back up to here. For example, Mercury is at about 0.4 astronomical units. Venus 0.7. Mars is 1.5. So roughly, right? Jupiter's a little more than 5. Saturn is 9.5. So and so forth. Okay, so that's a very typical unit that we use to measure distances within the solar system. Actually, the first time that we measured distances very accurately. So this is using AUs. You don't actually have to know what that actual distance is. We know what the distance between the Earth and the Sun is now. We know that very, very well. But certainly, back during the time of Kepler, we did not know that. It took a while actually for us to measure this, and the very first way that we measured it was using triangulation. Okay, and triangulation is the same kind of method that is used, like when you see surveyors along the road measuring with their the little telescopes, and they're measuring what's called a baseline, and they try to figure out how far away things are, from each other. That method has been used actually. Triangulation is for thousands of years. All right, so that was the very first. And since then we've used radar as well. We've bounced radar off of the planet Venus and gotten very accurate measurements. Of course, since then, we've actually sent spacecraft to orbit Venus and to take lots of nice pictures. All right. Anyhow, actually, they used radar to break through the clouds, to see through the clouds of Venus, because you can't really see the surface of Venus. Anyhow, that's a different story. We'll get to that later. All right, and then we get to Isaac Newton. So this is really when, the Kepler's laws, you can see, are mathematical, somewhat mathematical. Newton really lays down the foundations of what we would now call astrophysics by coming up with, and really physics as well, or at least the beginnings of what we would consider physics. He came up with his laws of motion, and so let's go over some of those. So the first law is very, you've probably seen it before. Objects at rest will tend to stay at rest. Objects in motion will tend to stay in motion in a straight line with a constant speed. So the thing is, if an object changes from a straight line, so if it curves, or if the speed changes, you need a force to do that. And the second law is, these are the laws of motion, okay? Not to be confused with Kepler's 3 laws, which are 3 laws of planetary motion. All right, so let's make sure that we get that. All right, so this is what Newton came up with. This is just a variation of what Galileo had actually observed. All right, so that's the first law. The second law, it says exactly how is the change in velocity, which is also known as acceleration, right? So that's what acceleration is. It's a change in velocity. How is that related to force and mass, right? And so this equation, traditionally you usually say F equals ma. So the force is equal to the mass times the acceleration. All right, so that's the second law. The third law is it's a little bit different than the first two. So in the third law, you're dealing with forces on different objects. So if you have object A, like for example, you push on the wall, right? So let's say you just put your hand on the wall and you push. Then what happens, what Newton's third law tells you is that the wall is actually pushing back on you with an equal and opposite force. So the force is in the opposite direction. You push on the wall, that's in one direction. Whatever the units of the force happens to be, you could use pounds. Traditionally, we nowadays in SI units, standard international units, we use newtons. And so if you're pushing, with 100 newtons in one direction, then the wall is pushing back on you with 100 newtons in the opposite direction. So that's the thing that's important about that. He also worked out what's called the universal law of gravitation. Of course, people knew about gravitation. Remember that thing I said before about Galileo looking at the moon and talking about how there were valleys and mountains on the moon and that it kind of looked like the Italian countryside? I think that idea got into Newton's head, and so Newton lives a good generation after. He was actually born the year that Galileo died in. Let's see, when was it? It was in like 1642, if I remember correctly. Anyhow, that doesn't really matter. So certainly people knew about gravitation, but they didn't realize that gravity is a universal force. It doesn't just apply to the Earth. All right, and so and of course Newton worked out the mathematical relationship between the gravitational force. So there's the equation right there that I'm pointing the mouse at. So the force is equal to a constant G. Big G is an important constant in the universe. It's the universal gravitational constant. And then the product of the two masses divided by the distance between them squared. So the gravitational force weakens as the square of the distance. That's what this graph is telling you. All right, so there it is. There's the universal gravitational force, of course with the constant. And the constant wasn't measured during Newton's lifetime. It was measured much later by a guy named Cavendish first. All right, anyhow, so let's move on. So Newton's laws were actually Newton applied them to measuring things like the mass of the sun and the motion of the moon. So for example, using Newton's laws of motion, there's the mass that's actually the current value, the accepted value of the mass of the sun, 2 times 10 to the 30th kilograms. And he also worked out this thing called escape speed or escape velocity. So how fast does something have to be traveling to leave the Earth and never come back? And if it's going slower than that, it of course either comes back to the Earth or it'll go into orbit. But to leave the Earth and never come back, that's called the escape velocity or escape speed. Newton actually worked out the value of it. It's actually more than 26,000, or right around 26,000 miles per hour. So it's not an insignificant speed at all. And of course, it takes rockets to be able to reach that kind of speed, right? And you can't, throw a ball up into the air anywhere near 26,000 miles per hour. All right, so that is it for Chapter 2. The rest of this is just, what we just went over, the summary of it. All right, very good.